So, what we're going to be talking about today is the early prehistoric universe. Prehistoric in a very loose sense because we kind of lose track of time the further we go back. So, what we're going to do is walk back in time and just take a look at what we know about the origins of the universe and, just as importantly, why we know that. Now, especially for your group, I feel like this might be relevant because there's a lot of creation stories out there, and there tends to be this particular topic is a magnet for criticism. Um, there's a lot of kind of what I would consider silly arguments, like if you weren't there, how could you know? And it's very dismissive of the hard work that scientists do to reconstruct the early universe and piece together the forensics and the clues left behind. And the process of discovering the earliest known state of the universe is a very fascinating topic. And there's so much more than we can cover today, but we want to give you an overview of what we know happened and how we know that came about. So, in general terms, I think it's important to understand that there is not direct evidence for a lot of features that we're going to be talking about, especially at the earliest time intervals immediately after the what we'll loosely refer to as the singularity of the Big Bang. A lot of what we know about that comes from physics constructed or reconstructed at places like the Large Hadron Collider and other particle accelerators, where they smash bits of matter together, see how they break apart, and try and reverse engineer the physics that allowed that to happen. So there are clues in what we see today in modern cosmology and modern astronomy. We can observe the universe in its current state, and it's in motion, and it's expanding. And we'll talk much more about that in detail. But as it expands, we can, in very basic terms, say, well, what happens if it wasn't expanding? What if it was restricting itself? What if it was going the other way? And so as it constricts backwards, it all converges to a single point in time and space. And the physics of exactly how that happens is mysterious. And again, for your group, I think that's important to understand that when something is not known, that doesn't mean it's impossible. It just means we don't know yet. And so I've heard a lot of anecdotal criticisms of the Big Bang Theory saying, well, if you don't know, if scientists can't piece together exactly what happened, maybe that is exact evidence for a god or a deity of some sort. And the proper answer to that is we don't know. We're just still figuring that out as a scientific community. That's something that is very interesting and the focus of a lot of modern research. And who knows? We're making headway all the time. This is just an incredible time to be alive. So I think that in our lifetimes, it's very possible that we could have major breakthroughs, and we push back the veil of the origins of the universe even further. One of the next big steps that we are just on the cusp of reaching right now is the launch of the James Webb Space Telescope and the first science images coming back from that. You'll see later on exactly how it fits into this picture, but it is going to be capable of peering back behind or further back in time than any piece of modern equipment that we have. And so that is
Aric,
incredibly exciting. Yes, question.
uh, on this graph here, it says at the bottom, Big Bang expansion 13.7 GYR. What's the G?
Giga.
Giga. Yeah.
Uh, but it isn't okay, the expansion has taken place over 13.7 giga years. Well, what's a giga year?
Well,
1 billion.
yeah, giga is just another a way of saying a billion. Some
Oh,
people
okay.
say, some would use a capital B, and then YR for year. But we're using the convention of the giga because that's what most scientists, what most cosmologists and astrophysicists use.
Thank you.
hmm So with that, let's go ahead and walk through the different eras of the Big Bang, and we'll talk about a little bit more about how we know that along the way, and some of the methods used to reconstruct the early universe. So at 10 to the minus 43 seconds, this is called the Planck era. This is the earliest and smallest meaningful unit of time that we know about. Before that, we don't have a model of physics that can explain what's going on there. That's essentially the point where the macro scale physics that we use to describe how big things move and behave, and then the small scale, the quantum world, if you will, that tends to break down. We know that they must agree somehow, but there is a mysterious marriage between the two that is not understood. And so this is where we have the focus of a lot of research. But at 10 to the minus 43 seconds, and let me clarify the exponential notation in case you haven't seen this before. 10 to the minus 43 just means 10 with 43 zeros after it, so 43 decimal zeros. So it's a very, very, very small unit of time. Now, if you're wondering how we know that, this is based on the decay rates that are measured by smashing bits of matter together in particle accelerators. This is not from a direct observation, but we know that the physics can only behave in one way based on these types of experiments.
Aric,
So, yes.
Aric, just a little correction here. I don't want people to get confused. When you see 10 to the minus something, that means that it's 0.000. The number of zeros before you get to the first one, or whatever the next number is the minus 43. So minus 43 means 0.000, 43 zeros before you get to the first non-zero value. If it's a plus value, that means that you put the zeros after the number. So for instance, 1 billion is 10 to the ninth. So you write down a 1, and then you put 9 zeros to the right of it. So that's how it works. The minus means put the zeros to the left, put a decimal point, and put the zeros right after the decimal point before the number. And a plus means put the zeros after the number. So minus is very, very, very tiny. Minus 10 to the minus 43 is inconceivably, well, I can't even imagine how tiny that is.
Yeah.
And so I think what you said, Aric, was that you put the zeros after, and that's true if it's a plus number, which we'll see plenty of plus numbers, but the minus means 0.000. Those number of zeros are the 43 zeros. So just so small that, I mean, let's face it, none of us has a concept of that tiny as a time.
Yes. Yeah. Thank you for catching that. This is a good point to bring up the term astronomical. When we say astronomical scales or astronomical numbers, we had to basically use that word to describe things that we have no intuition for. Human intuition exists on a very, very small scale, and there's a point when we become saturated with the scale, and there is just no difference between immensely large and immensely larger than that. They don't have a meaningful distinction to us, which is just a product of the way our brains have been adapted. But that is one of the points that's going to come up a lot. We're going to deal with incredibly small and incredibly large figures, and just don't rely on your intuition for this subject. If your brain hurts by the end, that probably means you're following as close as anyone can. Okay, so let's move along. The next step is 10 to the minus 35 seconds. So this is when the cosmic inflation creates what's known as the quark-gluon plasma. Now, if you're following along in the image, we're going from left to right in the image here. This is the Wilkinson microwave anisotropy probe. This is an image from NASA, but just follow along and I'll walk you through the timeline here. So protons and neutrons don't exist yet, just leptons and quarks. And we know the quark soup here exists because of the conditions that have been replicated inside particle accelerators. And it's this early quark soup that likely gave rise to dark matter. Now, the quark soup is likely the phase in which matter gained superiority over antimatter, meaning that for every billion quarks of matter, there was antimatter, there was a billion plus one quarks of matter, which means that we have matter versus antimatter in the universe. and thus the universe can exist in its physical form as we know it today. Very, very small balance, but it tips in favor of matter, and that is incredibly important for us. So moving along, we have 10 to the minus 5 seconds. Protons and neutrons are formed now from quarks. This is the first 300 seconds of the existence of the universe. We have the elements helium, lithium, and even heavy hydrogen that have formed by nucleosynthesis. Let's see. Let's move along now to 380,000 years. This is when the nearly uniform soup cooled to about 300 degrees Kelvin. So atoms formed nuclei and electrons. So photons ceased to scatter and streamed through space unhindered. And the universe, which was priorly opaque, now became transparent to visible light.
That's, Aric, you said 300 Kelvin. It's 3,000 Kelvin.
Sorry.
Yes. About the temperature of the surface of a red giant.
Yes. Very different. Yes, 300 would be nothing in comparison. So then moving along to 380,000 years, this is a period known as the Dark Ages, and this is the front edge of cosmology right now. We just don't know a whole lot about this period. This is one of the eras that the James Webb Space Telescope is going to peer much closer to. So it's going to verge right on the edge of that, closer than we've ever been able to see before. Then moving along, at 100 million years, this is the limit of our current observations. This is the highest redshifted objects that are detectable are at a time when it was about 600 million years old. And this is where future projects like the James Webb, which is coming online right now, the Roman Space Telescope in the future, the Square Kilometer Array, which I'll show you later, they're designed to shed some light on this era, and maybe we'll peer behind that just a little bit more than we currently can. About 9 billion years after the Big Bang is when our solar system forms. Now, it's important to note that our solar system is not special. It wasn't one of the earliest solar systems. There's really nothing unique about it from what we can tell. Estimates are that our sun is a third-generation star, meaning it's comprised of matter that has been incorporated in at least 2 prior suns like our own or similar to it. But our sun is not the first of its kind. It's made out of old star material, given rebirth through some processes that are beyond the scope of what we'll talk about today. But our solar system formed about 9 billion years ago, which is still incredibly early if you think about it. It formed roughly about as soon as it could have, even though it wasn't a first-generation solar system. Then 10 billion years ago, this is when dark energy, which we still don't really understand, seems to have begun to accelerate. And this is one of the processes that's going to cause collisions with different galaxies. And I think we've mentioned this before, but estimates right now are that we are headed towards, or the Andromeda galaxy is headed towards us. So we will eventually merge and collide with the Andromeda galaxy.
Excuse me, Aric.
Yes, go ahead.
I'm already confused. Okay, when you said 9 billion years and now 10 billion years, are you talking about after the beginning of the universe or 9 or 10 billion years ago?
9 or 10 billion years after the Big Bang.
Okay,
Yeah,
right.
Time equal to 0 is Big Bang. So Aric is counting, not counting down like a launch, but he's counting up to our current time epoch, which is about 13.8 billion years after the Big Bang.
Yes, exactly. Mike.
I was also thinking as you go from left to right, from the very beginning of the Big Bang towards us, the universe is always expanding from that tiny little point where it started, right?
Correct.
Okay.
We'll talk even more about that in just a moment. This is such a very bizarre concept because there's really no analog for this type of growth in our daily lives. So it is a little confusing. It's still kind of a mind-bending subject to think about. So here's another graph that explains, kind of recaps just what we've seen. Time equals 0 is on the left, and then structures become more advanced. We have the formation of the first stars. Then we have early matter coalescing into galaxies, and the galaxy structures become more advanced as we go through time up to the present moment. So peering back in time and in space, both distance and time, time and distance become kind of two sides of the same coin at a certain point. The earlier back we look in time and distance, the simpler and more primitive the structures become. And that is one of the main reasons why scientists are interested in peering far away from the Earth, because the further back we look, the further back in time, because the light is yet to reach us in its current state. In fact, there is really no such thing as real time. It depends on where you're standing in the universe. There's no one global universal time frame that applies to everyone. In fact, every single person carries with them a slightly different time scale or time frame, just because it takes a moment for everything to reach you. Sound and light, they both travel at finite speeds, and so there's no such thing as perfect real time synchronized for everyone. It's all dependent on the observer. But for small distances and short times, it's not an effect that we ever notice. But when we're looking back in time, that is what gives us clues to the early universe. And so that's why scientists are interested in looking far away, because we're looking further back and we can see the more primitive, simpler, earlier structures in the universe. One great way of visualizing this timescale is to conceive of what Carl Sagan deemed the cosmic calendar. And so I'm going to let Neil deGrasse Tyson explain it visually for us, because I think he does an excellent job. So let's just make sure that the sound works, but let's just watch this brief clip that hopefully helps clarify what's going on.
This cosmic calendar compresses all of the last 13.8 billion years since the Big Bang into a single calendar Earth year. Every month is a little more than 1 billion years. Every day, a little less than 40 million. A single hour is almost 2 million years. That first day of the cosmic year began with the Big Bang, almost 14 billion years ago. Nothing really happened in our neck of the universe until about 3 billion years later, March 15th, when our Milky Way galaxy began to form. 6 billion years after that, our star, the Sun, was born. It was August 31st on the cosmic calendar. Jupiter and the other planets, including our own, would soon follow. The atmosphere on Earth was a toxic environment for our kind of life. Then, September 21st on the cosmic calendar, tiny creatures that could shrug off the methane and eat carbon dioxide and sunlight for breakfast found a way to make a living in the ocean. By gobbling up the carbon dioxide and giving off oxygen, they turned the sky blue. And then, the oxygenation of the atmosphere created the ozone layer. For the first time, life was free to leave the oceans for the land. Now, life could grow larger and venture forth into new territories. Sometime on December 26th, about 200 million years ago, the first mammals evolved. They brought a new feature to life on Earth, the neocortex. And then, late on New Year's Eve, a mutation occurred in the DNA of just one of our ancestors. One base pair of a single gene programmed the neocortex to grow larger still. Maybe it was a random zap from a cosmic ray, or a simple error in transmission from one cell to another. Whatever it was, it led to a change in our species that would ultimately affect every other species of life on Earth. By the last second of the cosmic year, there was no place on Earth that we had left untouched. All of it comes down to nothing more than a single rung on our tiny DNA ladder to the stars.
So, plug for Cosmos if you're interested in that. There's plenty more. And Neil deGrasse Tyson does a really good job of explaining that. He kind of inherited the project. He's you could say, the spiritual successor to Carl Sagan's original Cosmos, which I would highly recommend if you haven't seen it. But both of them are great. The modern version, the not remake, but the current iteration of Cosmos is just a fantastic show because it covers all these sorts of topics in great detail. As you've already noticed, it's somewhat hard to visualize a lot of these concepts, and I think they do a fantastic job with the animations, explaining a lot of the more esoteric concepts visually. They lay it out very nicely, and it incorporates a lot of the most recent findings. So check that out if you haven't seen it. I'd highly recommend it.
Aric,
Yeah,
if I raise my
This co-
virtual hand, do you see that?
I do. Yeah.
Okay, this may be a stupid question, but was there actually a bang? If there was some way for us to be there at the time, would we hear an incredibly loud bang?
Well, there's a lot to unpack in that question. That's a fantastic question. Um, there was no way for matter like we know it right now in its present state to exist, so there was no place to be in which to even witness this, because everything in the entire universe was contained in an incredibly tiny space, much smaller than a pinhead. Let's see, Ron has some interesting ideas on this too. Let me let him field this question if you don't mind, Ron.
Yeah, well, that's a that's a very good question, and let me just say that I understand the spirit of the question. Um, we humans with our ears would not have survived in the if we were there at the time, we would not have been able to survive in those temperatures because they were um, gigakelvins. It was so hot and dense that our structures of the ear couldn't exist. But the spirit of your question is, um, laying that aside, would there be sound waves? And I think there were sound waves. Yes, there were sound waves. The matter energy stuff had energy pulsing through it, and those some of those energy pulses would be sound waves. And one of the things that astrophysicists would like to do is uh, to correlate the cosmic microwave background, which we'll talk about in a little more detail later, the the anisotropies of that, the fact that it's not a uniform field, they would like to relate that to sound waves in the just after the Big Bang or in the Big Bang. The Big Bang is not a great name for it because it wasn't an explosion. It was the creation of space-time and the moving out of that creation. And so it was a flow, a movement, but there was no explosion because there was nothing for the explosion to go into. It was everything that was part of the initial creation of the big of the I guess the Big Bang. So it's not a good name for it, but it it stuck. I'm afraid we're up against the wall of our own thought concepts and language, not being able to um, get a precise handle on what the Big Bang was. So that's why I'm flubbing around a bit here. Is I'm trying to put language to what is an ineffable event in the creation of the universe. And I don't think English language can really describe what it was.
I appreciate that. Thank you.
Mm-hmm. Thanks, Ron. I have two different conceptions of the cosmic calendar, and I think it's helpful to visualize. It really is striking how recent life on Earth evolved and where we are in that stage. Just like Neil deGrasse Tyson was explaining, this all happens the last few days of the calendar year. If you were to compress the entire scale of the universe, 13.8 billion years, to fit in 365 days of an Earth year calendar. So this just kind of recaps that. A more detailed graphic, which I'm afraid might be a little bit below the threshold of resolution here on your screens, this it basically paints it out in a spiral fashion, but it shows the same set of information just from the origin of the Big Bang, and then time spirals outward. And you can see in a little bit more detail the different processes that created the galaxies, then our solar system, and then life on Earth. So this highlights key events, but it's just another way of visualizing it, which I think is very interesting. If you're interested in seeing this graphic up close, just send me a note after this. We can get in touch via Meetup, or I can give you my email address if you'd like, and I'm happy to send you the full resolution version of this.
Hey, Aric?
Yes, a question. Go
We got
ahead.
a question in the room. Jared, if you want to ask something?
Oh, it would be good for their presentation purposes to know the story of the Big Bang, which came from Fred Hoyle. And you may recall that Fred Hoyle was a very, very smart guy and invented nuclear genesis, whatever you call that. He's responsible for that. But he was a static universe guy, was not going to give up on the static universe. And he called it derisively the Big Bang. And everyone said, oh, that's a good name. Let's just go with Big Bang.
Yeah.
Yeah.
Yep.
So they could have called it the GB, the Great Beginning, or
Oh,
but
even better. Jesus knows, maybe.
But you're right. Fred Hoyle thought that the whole concept of a Big Bang was ridiculous. He was a steady state theorist, and he wanted to, as you said, derisively refer to this other theory with a name that just reduced it to something that seemed ridiculous even in the name. So he called it the Big Bang. Well, the Big Bangers liked that, and and they stuck with it. And so he actually gave the name to his opponent theory. By the way, Fred Hoyle's steady state theory required that the universe constantly create matter and energy out of nothing. So the Big Bang seems to create matter and energy out of nothing in one big event. But what he was doing in his theory was creating in little bits scattered throughout the universe continuously. So which theory is more ridiculous than the other? I don't know.
We're working on that with quantum mechanics, though.
Right.
So basically, the Big Bang is the punchline of a joke.
Yes, exactly. So we're talking about a big joke today.
Which makes it better for a comedy show.
It is such an absurd concept. That's why I think it's so fascinating to understand how these results were obtained, because as Carl Sagan also said, extraordinary claims require extraordinary evidence, and there is extraordinary evidence. This is one of those cases where we can get back to a certain point, but it's not easy, and I think it's a little, like I said earlier, it can be dismissive of the work that scientists have done to work back as far as we have, even though the more interesting part still lies ahead of us. So again, who knows what will be discovered in our lifetimes, but probably we'll get closer to it, and that's the process of science at work in front of our eyes right now. Okay, Ron, do you want to mention a little bit about the expanding universe here?
Yeah. So the two most important things to say about the universe as we know it is A, it's big, and B, it's expanding. And back in the 1920s, the universe was thought to, in the early 1920s, the generally accepted view of astronomers was that the universe was the Milky Way galaxy. And these fuzzy things that were called nebula were part of the Milky Way galaxy. So by the time the 1920s were over, we knew that the Milky Way was just a tiny, tiny piece of the entire universe, and that there were hundreds of trillions of other galaxies like it, some bigger and some smaller. So the universe expanded, by a trillion times in that decade of the 1920s. And also during the 1920s, and part of of our understanding of the universe. Once we understood the scale of the universe, someone named Edwin Hubble, who was working with the largest telescope of the time, which was Mount Wilson, just in the San Gabriel Mountains north of Los Angeles. He discovered that once the distance scale was set, he discovered that the further away a galaxy seemed to be, the faster it seemed to be moving away from us. And once that was verified, the universe was accepted as being not only extremely large, but also getting larger all the time. And the expansion, of course, points back to the Big Bang. And this is one of the reasons that this is one of the big pushes for the Big Bang becoming the ascending theory of the evolution of the universe, was because all points led back to one point. And this, so when the top picture here, which shows the galaxy getting larger, first it's red hot and it's cooling and cooling and expanding, is not a very good picture. So I put a bottom picture in here too. Why isn't the top one a good one? Because it shows the galaxies expanding along with the universe. And that's what you would get if one model of the universe is often take a balloon and put little marks on it, dots on it with your magic marker, and then start blowing it up. And the dots on the balloon get further and further apart as they blow them up, but also the dots get larger. Well, that's not the way that's not the correct model of the universe as we understand it. Those dots stay the same size, and the distance between them gets larger and larger. And that's shown better by the tinier picture with the red balloon there. If you notice that those marks for the galaxies actually stay the same size as the balloon gets larger. So at one point back in the past, the galaxies were closer together. Everything was closer together. And then as the universe expanded, those galaxies which remained, well, they continued to evolve, but they remain roughly the same size, with the distance between them increasing. And that's what the observational evidence that has been uncovered for the evolution of our universe. The distances between the galaxies get greater and greater on average. That on average is very important, as we'll see later.
One interesting thing to point out here is that this leads to what might at first seem like a paradox. We can measure the distance across the universe at, what is it, around 100 billion light years across. And you may wonder how that's possible if light has only been free-flowing for about 13.8 billion years. And if nothing can travel faster than the speed of light, how is it that it traveled that far? Well, the answer lies in the fact that the universe is expanding, so the space upon which it's moving through is carrying it faster, so it's stretching as it goes. So it's not traveling faster than the speed of light in its own time frame, but that light is traveling through space that's moving, so it is stretching it, and therefore it's able to cover more ground than it could if it was just going at the speed of light in a static frame.
Yeah, the speed of light, or c, I say c instead of the speed of light because, as you know, the speed of light changes if it's moving through a material medium, and c is a constant, the speed limit of the universe. But it turns out that space-time can expand faster than c. There is no material bodies in the universe can't travel faster than c or even at c. But the expansion of space-time doesn't care about that speed limit. So there's a point at which we can't see parts of the universe, of our expanding universe, because the universe is expanding faster than the speed of light. The light can't make any it can't get to us because it is being stretched out, and the distance between it and us constantly, it's expanding wave fronts, and our location is increasing faster than those expanding wave fronts. So it's, as Aric said at the start of this is bizarre to think about, but that's where we are.
Another important concept to maybe add a little bit onto here is the difference between linear and just speed and acceleration, I guess. So when we say the universe is expanding, Ron mentioned that the further we look away, the faster they appear to be moving. So the universe is accelerating. It's not just expanding at a constant rate. The difference between acceleration and speed, if you want to think of it this way, when you get in your car and get on the highway, you're at rest at 0 miles an hour, and then at highway speed, you're at 60 miles an hour. Now, 60 or whatever speed you're at, I'm sure you all drive the speed limit, so we'll say 60. That is a constant speed, so you don't feel anything in your frame of reference from the car. Once you're at highway speed, you don't feel like you're being pushed back in your seat. You're just going at 60 miles an hour, but it is constant. There's no more acceleration. Now, acceleration happens when you change speeds. So that's like going from 0 to 60 in a few seconds. What you feel is that change in speed, basically the inertia of your body pushes you back against the seat, or so it feels like that from where you're sitting, because the frame you're sitting in is accelerating forward. The universe is doing that. It's accelerating. It's not just expanding at a linear rate. So the further away we look, the faster that speed is. And the steps in between are constantly growing. So the steps themselves are moving and stretching further and further the farther we look away from Earth. Now here's an interesting question. Yes, question.
Well, I would like to delve more into an argument from the opposite perspective of what you're talking about, the expansion of space-time. How do you reconcile your speed limits with quantum entanglement?
That's a good question. Quantum entanglement. I'm not as familiar with that. Ron, maybe you have a better idea about this?
Yeah, quantum entanglement, there's different explanations for that. And it appears, though, that it is possible for information to flow faster than the speed of light, and faster than c. And at least that's one interpretation of quantum entanglement. Another,
Is that, are you putting that within the context of space-time?
yes.
So you're saying that you can have superior relativistic speeds within space-time?
Well, I certainly would never rule that out. Tachyons are still which are particles that travel only faster than the speed of light, are still bandied about as a concept in physics. And so I certainly wouldn't rule that out. But the quantum entanglement has to do with our with our state of knowledge of things. And so there's another interpretation which says that it's not really related to the speed of light, but it's just our state of knowledge of things. And like two entangled particles, if one is uncovered here and is in a certain state, then we know the other one is in a, maybe it's halfway across the universe, it must be in another state. And that's a thought experiment, and probably couldn't be done in actual well, I don't know how you would do that experiment, because there's so many things that can go wrong. As you know, quantum entanglements are in practice very, very hard to get and to keep. over any period of time. They decorrelate so fast because of random motion of particles and stuff. So I don't know how you would actually do that experiment to find out whether that's true or not, because any quantum entanglements that we create last milliseconds, or some of them have lasted a second now, but they're really hard to last for a long period of time, especially if particles are moving through space where they can bump into things. Any tiny bump decorrelates them and they're no longer entangled. So that's an open question, and just like the question of tachyons, and my mind is open to either thing being possible.
All right. Well, thank you for that, Ron. Let's talk about the Hubble constant. So, Ron, I'll turn it over to you.
Yeah, so talking about things that we can measure, back in the 1920s, the Hubble and others measured what they started to get a handle on cosmic yardsticks. They saw all these objects in the telescope, but how far away were they? You don't know how big they are until you know how far away they are. And before the 1920s, they thought these fuzzy things like the one you see here, these nebula, were actually in the Milky Way galaxy. And then they started to find out about variable Cepheids and their distance away by measuring things in the small Magellanic Cloud, and then they discovered, and then they correlated that to supernovas, which are very bright and sometimes get brighter than in the entire galaxy that they're in. And so they were able to piece together the cosmic ladder of distance. And once they could do that, they discovered that the further away an object was, now they could measure the distance more reliably, the faster it was receding from us. The recession is determined by the spectra. As you can see here, there are two dark bars in that spectrum of this fuzzy body. And those bars are compared to the emissions from an object which is in our rest frame, like a glowing gas, and they see those same two lines, but they appear at a different they appear at a different spot in the spectrum, a different wavelength in the spectrum. And as you know, that's called redshift. The further away an object, the faster an object recedes from us, the more light energy, the more the wavelength of light is stretched, or the frequency is decreased toward the red. And so if you measure that displacement in the spectrum, you can correlate that to a velocity. If something were moving toward us, the opposite would be true. It would be blue shifted. But Hubble noticed that things, the further away they were, the more they were redshifted. So the velocity that he measured was equal to some constant times the distance they were away. That constant, over time, it's changed a lot over time, and there's still disagreement today, but it's called the Hubble constant. And I show it here as 70 kilometers per second per megaparsec. So if it's a megaparsec away from us, it will be receding from us at 70 kilometers per second. And proportional to if it was at twice that, if it was at 200 megaparsecs away, it would be 140 kilometers a second, and so on. A linear relationship with the Hubble constant as the constant of proportionality. So what is the Hubble constant? Well, it's got weird units, as you can see. It is kilometers per second, that's distance over time divided by distance. Well, distance over time divided by distance is 1 over time, or inverse time, a frequency. Well, if we take the inverse of the Hubble constant, then 1 over time should be a time. And we get something called the Hubble time. let's do the calculation. And 70 kilometers per second per megaparsec is when we do the calculation is take the inverse of that is 13.6 billion years. Well, it's very close to what we think is the lifetime of the universe. We said 13.8 years. Why is it not exactly the same thing? Well, things aren't quite so simple. The Hubble constant is a constant for now, but that doesn't mean that Hubble constant, the Hubble value has always been the same. We call it the Hubble parameter, and it at the bottom of the view graph, you can see we call it H of T, which means the Hubble parameter as a function of time, and that's changed over the history of the universe. But right now, it's called H naught, and that's the Hubble constant. Now, another interesting thing, what if V is equal to C? What if we look at an object far enough away so that the velocity is so high that it's actually equal to the speed of light? Well, that's called the Hubble distance. And that, as you can see, is 13.6 gigayears. It's the speed of light divided by the Hubble constant. Speed of light, meters per second, divided by 1/second. The seconds cancel, and you get a distance, and that's 13.6 giga light years. And so beyond that, beyond the Hubble distance, the universe is receding faster than the speed of light, and you can't see things that were visible before pass. They red out, and then they go into the microwave, and then they go beyond that, and then we lose sight of them. So parts of the universe that were all together during the Big Bang, we've lost sight of. They're beyond the horizon, the speed of light horizon. So we can't see them anymore. So that's kind of what the whole Hubble constant is. And I hope that just gives you a look at that. Here's the sort of thing that Hubble saw back in the 1920s. He saw on the left-hand side a galaxy with a certain distance in megaparsecs. A parsec is 3.26 light years. Astronomers like to use that, and there's a reason for that, but we don't want to take the time to explain that right now. I prefer light years, and I like to be a purist and just light years all the way through. But the most common way we see the Hubble constant explained is in kilometers per second per megaparsec. 1 million parsecs, so that would be 326 million light years. And you can see that the further away that the object Hubble observed was, that on the right-hand side was the velocity that he measured through the redshift in the spectrum of emission. And so an object at 20 megaparsecs was 1,400 kilometers per second. And then an object at 300 megaparsecs was at 21,600 kilometers per second. So if you divide velocity by distance, you'll find that there's always the same constant involved, and that's the Hubble constant. So that was the experimental evidence that was uncovered back in the 1920s and has been refined and refined over time as our distance measurements get better and better.
Ron, we had a question here.
Sure.
Yeah, Ron, I find it fascinating that that the Hubble constant is a linear function. With acceleration. And could it be that really, the objects in their relative space-time are not moving at all, but it's just simply that space-time itself is stretching? It would almost be like stretching a fabric. Is that a valid way to think about that, or is it much more complicated?
Well, that is a valid way to think about it. That's the way I think about it. However, it is quite a bit more complicated. The Hubble constant is a measurement of space distance or velocity space distance. So the velocity increases in a proportional way the further away the object is in distance, but that's also the further away as it is in time. And so to find out what the Hubble constant means in terms of a time derivative is a much harder thing to do. In fact, you have to know general relativity and you have to use Einstein's equations to truly understand it. And it's a very tough mathematical subject. So your question is very good, and it's right on the edge of a much more complicated way of looking at this and of describing the universe, which astrophysicists use, but it's not something that we could talk about today because I would have to talk about proper times, I would have to talk about co-moving times, and so there would be lots of relativity in it and some pretty complex equations. So, but very good, a very good question. You got the right idea.
Let's just look briefly at redshift. Oh, more question.
Would you be able to tell us when and where we might access that mathematical description?
Sure. Let's see. So you would find it in.
For somebody that flunked calculus.
Wow. I'm sure there are popular books about it. I wouldn't suggest that you start going through hard mathematical books of general relativity right now and look at Einstein's field equations, because solutions for Einstein's nonlinear field equations are highly advanced mathematical manipulations, which I can't do, and I have never learned how to do. So I'm not a good person to direct you, but I'm sure that there are a lot of popular books about relativity that would explain it in words. However, even for those books, I'm not sure they would treat things pretty much like Aric and I are treating them. And they wouldn't explain how you can get, for instance, from the Hubble constant in terms of a derivative of velocity with respect to distance to a derivative of velocity with respect to time, because time has so many different meanings in relativity. There is no universal time like Newton thought there was. There's nothing like universal time. Every single moving object in the universe has its own time scale, and they're on the surface. I say surface of this hyperspace, which is 5-dimensional. Space-time rests on the surface of a 5-dimensional hyperspace, and and it's expanding. The hyperspace is expanding, and it expands the space-time, the 4-dimensional space-time that we live on. And there's different theories about what the shape of or the metric of space-time is, and I've probably already gone too far, but I've just tried to indicate to you how complex the calculations are for relating observational measurements to a theory of the space-time metric and how it evolves in time. That's not even a set thing. As we get more in different observations, the models continue to change. So I could look up some popular books for you, but I'm not. But I hate to recommend things that I haven't read myself. And maybe, how about this? Go to, just to start out, go to Wikipedia and look up the evolution of the universe, and you'll dip into some of the concepts in just that short article. And then they have references, and you could go to those references. I'm not sure you'll be happy with that, but at least that's a way to start.
Are you in the Boulder cosmology group?
Did you ask if I'm in the Boulder cosmology group?
I did.
No, I don't know what that is. So
I was worried about that. I think you need to be forced to join the Boulder cosmology group.
Okay, well, I'll take that under advisement. I can Google them and find out how to contact them.
I was just going to put in, I was going to put in real quick for the popular books. Stephen Hawking's A Brief History of Time is probably one of the better ones, I would think.
Well,
and he is an
have read,
astrophysicist.
I have read that, but I just don't know. I don't know whether that would answer his question, because his question really is, how do we understand the geometry of space-time in terms of the evolution of the Big Bang? What's really happening, and how do we measure, how do we determine how long it takes light to go from one point in this expanding space-time to another fixed location in the space-time, when the space in between them is expanding and not necessarily even expanding at the same rate in time as the universe evolves. Very, very tricky and hard things to understand, because we don't even have the word time has a very squishy meaning in relativity.
Yeah, I think you're right with Hawking's. He probably does a pretty good job on explaining some of the basics you might need to understand that. But it's all pretty tricky, yeah.
Yeah, I find it so. I don't mean to be pessimistic here, but any person that has an interest in this needs to find their own level of interest in terms of how much work they're willing to put in to understand general relativity.
Hey, Ron and Eric, I don't want all of your time to be eroded on, maybe we spend enough time on this question. How much more presentation do you have? Because I want to make sure you've got enough time to get through it. Should we get moving, Andrew?
Sure.
What time do you typically want us out? We could go all day.
Yeah, you could go all day. I think so last time we were pushed for time packing up here. I think I want to wrap it up like 10 till 3 or something like that. So
Okay.
You got another 50 minutes or 40 minutes.
Okay. We'll maybe we'll aim to end a little after maybe 1:35, 40, and then we can just open the floor for more questions.
Yeah, okay.
Make sure we get everyone covered. Okay. That reminds me too, another book that covers a lot of the foundational topics is Neil deGrasse Tyson's Astrophysics for People in a Hurry. It's been a while since I've looked through that. From what I remember, it explained things pretty well, but it seemed like his version of People in a Hurry didn't match mine. It seemed a little bit dense. So there was another book that came out not too long after, and I don't remember the exact name, but it was something to the effect of Astrophysics for People in Even More of a Hurry, or something like that, that basically reduced the original book and made it even more accessible. So some combination of those two books you might find helpful just for recapping and going deeper into some of these subject matters without relying too heavily on a technical background.
Yeah,
Um,
that's very good, Eric. And I might suggest another book. It's a book by Kip Thorne called Interstellar, or The Physics of Interstellar. He was the science advisor for the movie Interstellar, and he wrote a companion book to explain the mysteries of Interstellar. And he actually, I mean, it's a good book to dip into all the different concepts of relativity, special and general, and yet in an entertaining way with lots of diagrams and pictures and stuff. So that would be, wouldn't you agree, Eric? It's a pretty mind expanding book.
yeah, it's great. I can't remember if we've talked about that movie with your group, but we've covered Interstellar a couple times and all the science that goes along with it. It's a very fascinating topic. They did a lot of work to get everything, well, not everything, but the important points were very accurately addressed in the film, and the companion book is excellent. And you don't even have to have seen the film for it to be helpful. So yes, highly recommended. Thanks, Ron. And then just another general comment, a lot of what you're maybe noticing by now is that even though there is some sophisticated mathematical descriptions of what's going on, it doesn't necessarily, there usually are ways to describe loosely what's happening. The reason physicists and scientists like to use mathematical descriptions is because it removes all the ambiguity and some of the more esoteric ideas that are far afield from our human intuition. They can be described mathematically with much greater ease, but that is a foreign language in a lot of ways, and mathematics isn't the only way to access these ideas. So hopefully you're understanding that while we're trying to describe in plainer English, I don't know if we're quite getting all the way to plain English or if there is a way to do that, but we're trying to explain ideas that exist in a mathematical root that are very clear and concise, and then we're trying to extrapolate that into words. But like I said at the beginning, intuition is not the greatest tool in this area. There's another quote, I think it's Neil deGrasse Tyson again, but he says, "The universe is under no obligation to make sense to you." And I hope that's becoming clear by now. And it probably always will be that case to some extent. Just a quick visualization of redshift that Ron was talking about earlier. As the universe expands, the light in between is stretched and it shifts towards the red end of the spectrum. So what you're seeing here is just a visualization of that. The spectral signature of this galaxy here, it's moving to the right and up a little bit. That's called its local motion. That's the motion relative to the source or the observer here at position A. But notice the two, and this might be a little bit small to see on the screen. Hopefully you can see my mouse there. There are these two spectral peaks. And now when we move down to position B, this accounts for the expansion of the universe in between the observer and that galaxy. So while that galaxy is receding away from us, the space in between us and it, the observer and the galaxy, is itself expanding, and that causes it to shift towards the red. And notice how that original spectral signature, the wave pattern in the box, that is stretched. It covers a wider horizontal distance than it did in the original. That is because of the expansion of the universe, causing it to shift towards the red. Now on a spectral signature here, the two peaks remain the same distance apart, but they have shifted towards the red end. So the patterns in the spectral signature are still identifiable, but they have moved. They've been transposed on the spectrum and shifted towards the red. And so the position C just combines the two. It shows the apparent distance from the local motion plus the expansion of the universe, and then the actual distance between is much, much, much greater. As it says there in the parenthetical, it's far off to the right of the screen there, because the recession speed increases with distance. So the further away it is, the greater the stretching is. This is one of the reasons why the James Webb Space Telescope is going to be so helpful, because it is tuned specifically to see in the infrared, and the further away we look away from Earth, the the further it is shifted into the red and the infrared. If it shifts far enough from the red, it crosses below the threshold that our eyes call the red range, and then we go into infrared, and that's where the James Webb is tuned to look specifically at very far objects that have been stretched significantly by the expansion of space-time. All right, Ron, do you want to talk about phases and changes?
Yeah, I don't know how much we should spend on this now, but Aric took you through the beginnings of the universe and the Big Bang and the evolution of the universe. And he talked about various changes that occurred as the temperature dropped. And I just wanted to point out, this is not often emphasized, but what he was talking about in the evolution of the universe is called phase changes. If you take matter and energy and you start cooling it, expanding it into a bigger space will cool it. The same matter and energy takes different forms, and that's called it's still the same matter and energy, but it just takes a lower energy form the colder it goes, and that's called a phase change. You're most familiar with the phase change of water, for instance. It goes from, at higher temperatures, it's a gas. If you cool it, it becomes a liquid. And if you cool it even more, it becomes a solid ice. Well, these are precisely the kinds of changes that we're talking about as the universe evolves. When hotter than gas is a plasma, that's when the water actually starts, some electrons get knocked off the water molecule, and you have ions, the electron being negative and the positive water molecule with an electron knocked off the hydrogen atom in the H2O, for instance, becomes positively charged. So each moving, as you cool down, you go from a plasma to a gas to a liquid to a solid. At some pressures, you can go straight from a gas to a solid. And that's called deposition. If you add energy, you're moving up this picture scale. And there is a phase, there's an energy that's given off or taken on between these phase changes. If you cool them and you go from a gas to a liquid, then energy is given up and it goes out as heat. Now, steam engines are based on going between a gas and a liquid water. That's the first engines that were built were steam engines, and that actually uses the heat of vaporization and condensation to run the engine. So the talk about the universe evolving, we're just talking about matter energy as it undergoes phase changes from a hotter environment to a colder and colder environment. It's crystallizing and freezing each different notch in the phase changes. The history of the universe is a history of cascading phase changes, is one way to put it. So I just thought that's not often what people talk about, but that's what's really happening. The same matter and energy, it's conserved, right? Matter energy is conserved. It's just changing different forms as it cools.
Ron, can I ask a question here?
Yes.
The concept of phase change or phase transition, would that be a reasonable way to describe what we call the Big Bang?
Yeah, in fact, there's a new paper that came out, and not that long ago, that says that the Big Bang itself may be a phase change. That prior to the Big Bang, there was this formless state of energy, and the Big Bang was a phase change from that formless state to a crystallized state of space-time that now makes up the universe. So it didn't come, so the energy in the Big Bang didn't come from nowhere. It came from a different phase of matter energy, which crystallized into the space-time universe that we now know. And all that energy was spilled into space-time as it expanded. So that's a new theory that was put out. So even the Big Bang itself was a phase change from a prior formless a state of the universe that we really can't picture and haven't described yet very much. But that's an interesting idea. And then what I've done in these next two view graphs is talk about the various phase changes, and from one to the other, where each phase change from one form of matter energy to another gives up energy in heat, but each phase is the lowest energy state that the matter energy can exist in at that temperature and pressure. A system, a macroscopic system always wants to fall to the lowest energy state that it can with those surroundings in that environment. And that's what the universe has done since its beginning, which might have itself been a phase change. It's just gone through this cascade of changes in matter energy to get to where we are today. And so I could talk about, Aric talked about the quark epoch, the quark gluon plasma stage. That was before there were protons and neutrons, so you couldn't even form atoms yet. And there was a phase change from the quark gluon soup to the quarks suddenly could combine, up, down became a proton, up, down became a neutron, and then the next stage could the electrons, which were always around, could combine with a proton and form an atom, a neutral atom. And in fact, I think it's on the next view graph, Aric. Yeah, so the recombination epoch is where the phase change, which is the furthest phase change that we can see. It is called the cosmic microwave background. It's when the electron-proton plasma, electrons are negative, protons are positive. It was a charged plasma. They were flying around and they made it hard for the photons of light. The photons of light would only propagate a short distance before an electron would scatter them. And so you weren't able to get form pictures of the universe because the light would only propagate for a short distance before it would redirect it. It's the same reason we can't see to the center of the sun, right? The center of the sun right now is where fusion is happening, and the photons that are emitted from two hydrogens fusing into a helium nuclei only travel a short distance before they get scattered. And they get scattered trillions and trillions of times before those photons get out through the surface of the sun. And so I think it's 100,000 years it takes a photon from the center of the sun to get out to the, so we can't form a clear image of the interior of the sun in photons with light because they're scattered so much. And that's what happened when the universe was an electron-proton plasma. The photons were scattered heavily by the electrons. But then it cooled down. Matter went through another phase change and became neutral atoms. That recombination epoch, where we went from a charged plasma to neutral atoms, mostly hydrogen. Now the photons, they don't scatter very much from neutral hydrogen atoms. They were able to travel millions of miles, light years, without being scattered. So the fog of the charged plasma slowly decreased as the temperature decreased, and the hydrogen atoms became neutral hydrogen atoms, and the fog cleared, and we started to see, we could see back to that era. And that's the furthest era that we've been able to see so far, and that's the cosmic microwave background, when the universe was 3,000, 4,000 degrees Kelvin, like the surface of a red giant star. That's what we see when we see the cosmic microwave background. We see that phase change to the neutral hydrogen atoms, and a few neutral helium atoms also. But that's a phase change that we're seeing. And the furthest one that we can see so far using light. Now, just a little teaser here. Suppose we had neutrino telescopes, which, by the way, we have. We would be able to, neutrinos don't care about plasma or anything. They go through the Earth without even being phased. So if we have good enough neutrino telescopes, theoretically, we could see through the cosmic microwave background, and we could see further into the past. Also, if we had better gravity wave detectors, we could see through the CMB, the cosmic microwave background, and see what happened on the other side of that, because gravitational waves don't care about plasma either. They go right through them, just like neutrinos. So in the future, with neutrino telescopes and gravitational wave telescopes, we might actually see beyond the CMB. But right now, that's the furthest that we can see. The universe at T equal 380,000 years, when that important phase change happened. So that's just a quick phase change explanation of the evolution of the universe.
So here is, let's spend a little bit of time on the cosmic microwave background. You've probably seen this many times, but not quite known what it is. So that's that slice of that blue and green soup-looking image. That is the phase change where the opaque fog of hydrogen plasma cooled down into neutral hydrogen atoms and became transparent. So this is the earliest, they call it sometimes the relic radiation of the Big Bang, the earliest that we've been able to detect. Let's watch a quick clip. I think this is a very good explanation of a recap of what we've covered and an introduction to the CMB as well.
Looking through a telescope is like looking back in time. Because light has a finite speed limit, the farther away you look, the deeper into the past you see. With radio telescopes, we can even see the universe as it was just after the Big Bang, nearly 13.8 billion years ago. But after that early snapshot, there's about 1 billion years we haven't been able to see clearly. Cosmologists call this the Dark Ages, and probing into this hidden era of the universe can tell us more about how it took shape, and even the nature of dark matter. First, let's take it back. Way back to almost the very beginning, about 380,000 years after the Big Bang kicked off this whole thing we call existence. That's the point when the free protons and electrons were cool enough to start combining into the simplest and most abundant of atoms, hydrogen. That's when the universe goes dark. Most hydrogen doesn't emit light in the vast majority of the electromagnetic spectrum. That's not to say it's totally invisible. It does give off and absorb electromagnetic radiation when its electron switches between two states, but at the relatively long wavelength of slightly over 21 centimeters. This means that if hydrogen gives off or absorbs radiation, it should be detectable, what's known as the hydrogen line. But plucking out the signal of ancient hydrogen from the rest of radiation that we constantly get bombarded with is tricky. Since it's traveled for such a long time to reach us, the space it's moved through has itself stretched out quite a bit, which in turn elongates the wavelength from about 21 centimeters to 1.5 to 20 meters. The longer the wavelength, the older the signal, and the deeper the redshift, the weaker the signal becomes, until it's easily masked by the noise from the Milky Way, or human activity like radio broadcasts, or even spark plugs in cars. Thankfully, the tools cosmologists use to see the history of the universe are getting better all the time. They're setting up radio telescopes and antennae all around the world, sometimes in remote locations to avoid human interference. like an island between South Africa and Antarctica, or on a lake in the Tibetan Plateau. New technology is making the enormous amounts of data these observatories churn out easier to analyze. Now, scientists think they can finally start sussing out what happened in the Dark Ages. There are 3 periods when hydrogen absorbed or emitted energy that should be discernible. The first occurred 5 million years after the Big Bang, when hydrogen cooled enough to absorb some of the background radiation, causing a dip in the hydrogen line known as the Dark Ages trough. About 200 million years later, the first stars and galaxies formed, giving off ultraviolet radiation that made the hydrogen more readily absorb 21 centimeter photons. This should appear as a second, more pronounced dip at a shorter wavelength. Finally, the third major event that affected hydrogen is called the Era of Reionization, or EOR. Around the universe's 500 millionth birthday, the UV radiation from stars and galaxies would have grown so bright that it would cause hydrogen to fluoresce, emitting 21 centimeter waves. But the hydrogen that was too close to the galaxies was bombarded with so much radiation that it was stripped of its electrons altogether. Separated again, the now free protons and electrons would go dark. So a snapshot of this time period would have ionized bubbles of darkness with brighter radiation in between. The EOR is the time period most experiments are investigating. One group of researchers in Australia recently announced that by using a new technique to process data from a collection of over 4,000 antennae called the Murchison Wide Field Array, they were able to generate a 10-fold improvement in their results, helping them hone in on when the EOR began. And just last year, an antenna in the Australian outback called EDGES may have seen the first glimpses of the ionized hydrogen bubbles around the first stars. The goal is to make a 3D map of these bubbles, and by examining different wavelengths, we'll be able to see exactly how the universe grew and evolved. Neat uniform bubbles will tell us that early stars were responsible for the reionization, while wispy, free-form bubbles will suggest the presence of black holes. Signals from the EOR could give us a clue about how to look for dark matter, indicating whether it's made up of sluggish and cold particles or warm ones that are lighter and faster. Before any of this can happen, though, we need to start finding that 21 centimeter wavelength in the data we're collecting. Once more arrays are online and more data is parsed, we might be able to shed some light on the universe's dark ages and the very first days of our galaxy. Another instrument that will search for the universe's first days is the James Webb Space Telescope, slated to launch in the early 2020s. Here's a How Close Are We episode on the...
Yeah, and you can check out more. You can see a little bit more detail than we've covered, but I want to...
Looking through a telescope is like looking back in...
So here is a comparison of how far back in time various telescopes have been able to look at. Given the time, I want to show you a visualization here in the planetarium program. So I'm going to switch screens, and we're going to look at the cosmic microwave background as it actually appears in the night sky, if we could see in the microwave. Give me 1 second, we'll just switch over. Give me 1 quick second. Here we go. Okay, so here is the night sky as our eyes would see it. And then that image that you've seen of the cosmic microwave background, that green and reddish ocean-looking thing, that is the map of the different temperatures of the cosmic microwave background. And this is what it looks like when it's superimposed over the entire night sky. Let's just zoom around so you can see it really does wrap around the entire sky. It's not tied to any one particular object. This is the background glow of the Big Bang left behind. So it's further than any of the stars that you can see or any of the galaxies. It's behind all of that before matter has, or before the first stars had formed. Ron, do you have any comments about this while we've got this screen pulled up?
Yeah, we often see the CMB picture just this way with these red and blue spots. Two things that I should say about that. Those, the irregularities in temperature have been massively expanded to get these kinds of pictures. The first pictures of the cosmic microwave background showed a uniform redness, if you will. There was no irregularities. It was all the same temperature everywhere. But astronomers and cosmologists thought, well, if we send up the Wilkinson microwave probe, so that we can look for any tiny variations that we could possibly have, because we're interested in using the cosmic microwave background to tell us about what was happening in the early universe. And so a background uniform map doesn't really tell us anything. We want to measure and look for the tiniest little imperfections so that we can use that to tell us about the way matter was clumping in the early universe, and the uneven distribution of matter, or the uneven distribution of matter that stood between us and the CMB, the dark spots that are kind of blocking the uniform redness. We're interested in that. And so they massively exaggerated it. So if they didn't do an exaggeration, you would see just a uniform red background for the cosmic microwave background. But ever since the Wilkinson and other studies, they're interested in the non-uniformities, so they always highlight those. But I don't want you to lose sight of the fact that there's very, very, very tiny irregularities that they're looking at. On a first look, it's just a uniform red background.
Yeah, and what is the difference in Kelvin? I think it's 10 to the minus 4.
Yeah, something like that. 1 part in 10,000 or something like that are irregularities, which in our everyday way of viewing things would be, there's no difference whatsoever. It's all uniform. But scientists are interested in any tiny differences that they can use to understand what happened before and after the CMB.
Well, let's see. I'm looking at the clock, and I want to make sure we have all of our questions answered. So we could talk a little bit more about the CMB, or we could take questions. So why don't we do a quick question pause here and see if anyone has anything they want to add or ask about, and we'll do our best. If not, we can just go for a few more minutes on the CMB.
I got a question, Eric, so when you show those pictures of the shape of the universe expanding, it's kind of like this bell-shaped horn type profile to it, but it's not linear, right? The edges of it aren't linear, they're curved. Is that curvature is a depiction of the variability of the Hubble constant? Is that correct? Is that the way to look at that?
Yeah, that's the Hubble parameter, the thing that was not H0.
Right, yeah, that right there.
Yeah. So if you go from the very bright spot on the far left, you'll notice that there's a fast expansion there. That's called the cosmic inflation. And that happens way before. That happens, I think it's a microsecond into the evolution of the universe. Suddenly the expansion rate just blows up. I mean, literally blows up. So the universe goes from a tiny quantum speck to something 10 to the 26 times larger in a very short time. And that's called the expansion epoch of the universe.
Is that Guth's theory?
I'm sorry?
Is that Guth's theory?
Yeah, exactly.
Superinflation.
Yes, yeah, yeah. There was this there was this scientist in Los Alamos who did his best thinking at night, and he would walk the streets of Los Alamos at night, and the police picked him up and took him to the station, and he had to be vouched for because they just couldn't understand an astrophysicist who walked the streets at night thinking about cosmic expansion.
So as we look at this picture on the far right, it looks like it's increasing, right? The rate is, it's not a linear line there, so.
Yeah, about 4 million years ago, the expansion rate started increasing again as and physicists explain that as saying that the dark energy parameter started coming into its own, and now the expansion is increasing again. Nothing like the original cosmic expansion, but if we measured the Hubble constant in another billion years, it would be larger than the Hubble constant today.
Yeah, I probably misunderstand this. I know very little bit about it, but so I think I've heard that the whole redshift thing is based on the color of something like a type 1A supernova or something like that.
Yeah, the distance
So,
scale, right?
so how do we know what the color of a type 2A supernova should be, and how is it? Why is it based on that one particular type of phenomenon?
Well, it's not the okay. So remember, to determine the Hubble constant, to measure it to begin with, or once you have the value of it, to determine how far away an object is, you need to have a distance scale. And the type 1A supernova allows us to get a distance scale which applies from our galaxy, from nearby galaxies, our galaxies, and takes us all the way out to to galaxies several billion years old. And then after that, we use distance measurements with cosmic expansions. But that distance scale was not it didn't exist before the 1920s, and that's why they thought everything was inside the Milky Way galaxy. That was the whole universe. And until this type 1A supernova, it's not really the color of it, it's the brightness of it that is related to the distance. The type 1A supernova is a special kind of supernova, which starts with a binary star system with a regular star, and circling it is a white dwarf or a neutron star. And that neutron star or white dwarf tends to steal material from the regular star, and that material falls into the white dwarf or the neutron star and increases its mass over time until it gets to the Chandrasekhar limit, 1.22 times the solar mass, and then it blows. The amount of mass is so great it can't support itself, and it contracts, and it is the largest thermonuclear device in the entire universe. You have a giant thermonuclear bomb with a calibrated amount of mass that feeds it. It's sort of a titration from one star to another. So every type 1A supernova has approximately the same megatonnage in it. And that leads to approximately the same kind of brightness. And so depending upon the brightness we observe and the brightness that we know was in the blast, we can determine the distance. And that goes all the way out. We see supernovas all the way out to as far away as we can see galaxies. So it's a very good yardstick to determine how far away an object is. Once we know how far it is, then the redshift can be measured, and we know where it fits in to Hubble's equation. So a type 1a is used as a distance scale, not as a wavelength scale or a redshift scale. It's used as a distance scale from which we then can derive either the Hubble constant or the distance away from any object. So we can measure the expansion of the universe once we have our yardsticks right. And type 1a is a good yardstick.
Anyone else, questions online or?
Just to add that I was wrong about type 2. It is type 1a, but they call it the standard candle for that purpose.
Yes, exactly. The standard candle. Astronomers are always looking for standard candles. Before the supernova were used, they used the variable Cepheid stars, and they were calibrated mostly to the small Magellanic cloud, and then we started using them to measure the entire galaxy and even into the Andromeda galaxy. But beyond that, they're just not bright enough. But type 1As are, so we can use those to go way further out.
Aric and Ron, I guess. We probably want to start with one.
Okay.
Was there any other last questions anybody had, or anything you want to say, Aric or Ron?
Do we have email available if they don't know about the Boulder Cosmology Group? That I would think that would be, they would be at home and in heaven there with books far beyond my ability to comprehend.
I had a comment. This has just been fascinating to me, and I'm glad there's been such a lively discussion. My guess is that you haven't covered as much ground as you intended to by this time. So I'm wondering if there can be a part 2 of this. Is it possible for you guys to come back and give us the rest of the presentation?
It certainly is, as long as you guys can encourage us enough. If we haven't wasted your time and you think maybe others might be interested also.
I think you can tell by the questions that we are very interested.
Yeah, we would be happy to. As you can see, there's no shortage of things to talk about here.
Conrad, can we arrange that?
Yeah. We'll talk about it on the board and with Aric offline and find a good time.
I can't hear you.
Okay, we'll find a good time for it. We'll talk about it on the board and find an appropriate time to schedule it and work with Aric to do that.
Just 2 parting thoughts. One thing that we've been talking about is maybe doing a star party with the Boulder Atheists just for you guys. So that is in the works. We haven't finalized a date, last I heard, but we are working on that. So you're welcome to come out for that. So just keep an eye out for an announcement whenever we get that arranged. We'll do just a private star party, so you guys can just have full time to on the telescopes. And then the other thing is that we have a total lunar eclipse coming up May 15th or 16th. I can't remember. It's in 2 weeks from now. So if you have any questions about that, please let me know. But there's going to be a lot of media coverage about that. We'll be hosting a few events at the local nature center here in Arvada. So if you have any questions or want to join, you're more than welcome. You don't need to be part of a group. You can just go out and look at sunset on that night. Right at moonrise, you'll see the full moon obscured by the Earth's shadow, and it'll turn a nice deep pale red and orange. So it'll be fantastic. It's a very rare, favorable lunar eclipse. Normally they happen very late at night or early in the morning. This one is very accessible, so be sure to keep an eye out for that. I assure you there will be no shortage of media coverage on that, so you won't need to hear it exclusively from me, but just, keep an eye out in the next 2 weeks for that.
And Aric, is it appropriate for our group members to contact you through your contact email on the Standley Lake Stargazing site? Is that
Yes.
appropriate to communicate?
I put my email in the chat. It's just Aric at Standley Lake Stargazing.
Okay.
You're more than welcome to reach out. I am a little bit swamped right now for the next 2 weeks, but after that, I will be much more reachable. I will save all your messages and I will get back to you. I wish I could be a little bit more responsive, but right now, just given time constraints with the end of the school year, I'm a little bit swamped. But I will get back to everyone.
Well, I certainly help, Aric. So if they send stuff just to you and you think it's appropriate, you can forward it to me, or you can send it directly to me and I'll be glad to try and answer questions.
Yeah, Ron, if you don't mind, you're welcome to share your email address in the chat too. And with your permission, I'll send it out in an email after this to Mike, and then he can forward it as appropriate.
Sure.
All right, well, thank you both. We really appreciate your time and the effort you put into the presentation.